This video gives an introduction to a first course in modelling, analysis and control. And first of all, we're going to look at dynamics. So a question for you. If I said build a paper aeroplane and your challenge is to construct this aeroplane to be the best that it can be, and you're going to have a competition, you're going to ask a number of questions. How do we define best? Do you mean distance? Do you mean how many loops it does? Do you mean longevity? Do you mean it's got to be straight? You're also going to be wondering what affects the plane performance. How do we measure performance? How do we undertake systematic design to improve performance? And what tools do we need to do all of these things and therefore do well in the competition? Now, here's a case study of something slightly different. A central heating system is given the following control law. If the temperature exceeds the target by 2 degrees, switch the heating off. If the temperature is 2 degrees too cold, switch the heating on. So your question is this going to be fit for purpose? How do you decide whether this is fit for purpose? What tools do you need to answer this question? Now we're going to give a quick illustration here of the sorts of tools that may help and the sort of questions you may then want to ask. So here's your house, and you can see I've put 2 in here, so that's the deadband for your plus and minus 2. So if I now run this simulation, and you'll see what happens to the temperature in the house. Look, it goes too hot, too cold, too hot, too cold, too hot, too cold, too hot, too cold, and look what's happening with the heating. 100% maximum power, switches off. 100% maximum power, switches off. Now, are you happy with this? And how are you going to decide? Now, there's things you can play with here. What if I make the deadband even bigger? So here I've now made it 3.2. And then you can see it goes even hotter and even colder. And probably you're going to be less satisfied. But the question I've got for you is, why are you less satisfied? What is it going on in your head that's allowing you to make that judgment about what is better and what is worse? Now, I could, for example, go to a PI control. Now, this isn't going to be good by any means, but run the simulation and ask yourself, is this one better? And you might look and say, well, yeah, I think that's better, but why? What has made that better than the previous ones? Okay, so we've been through that slide. And you'll see the core question here, how do you quantify what you actually want? And therefore, how do you compare different alternatives? So here's a second case study. A cruise control law is told that the accelerator position should be 0.08 times the integral of the error in speed. So will this cruise control do the job? How are you going to decide whether it's doing the job well enough or not? And what tools do you need? So again, we've got a little animation here to help you look at this. So if we find the animation, there it is. So here's our cruise control animation. So what I'm going to do is update the parameters and simply start the simulation. Now, what you can see, I'll pause it in a minute so you can see what's going on. That's probably about long enough. Oh, it didn't stop. Right, stop now. So here's the question for you. You can see what's happened to the throttle. It's gradually increased and it's gone quite high. And then it's come down a bit low, and then it's gone up again, and then it's gone a bit low. And what's happened to the speed of the car? It went too high, and then too low, and then too high, and then too low. So if we run that again, you'll see how the throttle's gone really high. See how the speed has gone too fast, and then the speed has come down. Now the speed's going up, and it's oscillating. All right. Now you might look at that and say, it's probably not very good. But my question for you is, why isn't it very good? Let's try a simple alternative. Now I'm not going to say this is perfect. I did stop that, but it didn't listen. So let's start again. I've changed some parameters. And now you'll see we're getting a slightly different behavior. Okay, hopefully that will stop before it disappears. And now look at the speed. You can see the speed only overshoots a bit and comes back. Now, is this better? And if it is better, why is it better? Okay. So, a third example. A large aeroplane has its suspension system designed mainly for landing. How would you select the appropriate spring and damper to ensure a comfortable landing for the passengers? And will this suspension system be fit for purpose? And again, how are you going to decide? And what tools do you need? So again, we've got a little animation here, so you can see the sorts of things you're looking at. And this is a bit more cartoonish, but let's not worry about it. So you can see there's the passenger of the aeroplane sat on the seat, and there's the suspension system. So let's run, and let's see this plane come into land. So there you go, it hits the ground quite hard. And what happens to the passenger? Look, they bounce up and down. Now, are you happy? You can see here passenger acceleration, initially quite high acceleration, then gets to zero, then acceleration in the opposite direction, and again some sort of oscillation, also in displacement. Are you happy with that? What happens if you change some of the parameters? So here's a different parameter that I might change. Now look at the numbers here. Acceleration went to about 1.5. Okay? What happens now with this different choice? Okay? And you'll see the landing looks a lot nicer if you're looking at the animation. But now let's look at the passenger acceleration. It went up to about 6, so 4 times bigger than what you had before. So which of those is better, and why? So a summary. Key questions we need to ask is, how do I define best? Is it the fastest behaviour? Is it the smoothest? Is it the one that uses the least control action or the least oscillation? How do I determine characteristics such as speed of response, convergence and oscillation? How do I actually calculate these? It's one thing looking at a graph, but I need to put a number on them. How do the response characteristics depend upon things I can choose or design, such as which spring should I use? What should the pipe area be, or the pipe length? What mass do I choose? And so forth. So this module introduces the mathematical tools and engineering background so that we can analyse, categorise and design real system behaviours so that the systems behave the way that we want and in a way that you might consider to be optimal in some sense.